Hey everyone. In the previous couple of videos, we talked about cases or interpreting linear regression models where the dependent variable was continuous. And of course, in a lot of our applied examples, the dependent variable is not actually continuous, but actually dichotomous. So it takes two different values, 0 or 1. One of the examples that we talked about in class, as well as in the assignment, was modeling turnout, for example, in the social pressure experiment. So here, the dependent variable is not continuous, it just takes two different values, 0 or 1. And the question is, of course, how does this change the interpretation of our coefficients in our OLS model, right? So in this case, we'll look at a quick example that involves such a dichotomous dependent variable. And a lot of the rules or a lot of the explanations that I gave previously regarding the interpretation of interaction effects and so on still apply. We're still looking at the effect of a 1 unit or the change in the expected value of y that is associated with a 1 unit increase in x. But the thing that is different now is how we interpret this change in the expected value of y, right? And so again, our example here, we have one dichotomous dependent variable y, we have one continuous independent variable x1, and again, I simulated some data with such a dichotomous dependent variable that is either 1 or 0, and a continuous independent variable, and also plotted this. So you see all the data points here are either 1 or 0, okay? So in this example regression, we have an intercept of 0.43 and a beta 1 coefficient of 0.16. So the question is now, how do we interpret these coefficients given that the dependent variable is dichotomous, so either 0 or 1, right? So if we turn first to our intercept alpha, we can interpret this intercept given a dichotomous dependent variable as holding all independent variables at 0. The expected proportion of 1s in y is alpha, right? And so why is that the case? Essentially, we're still similar to our continuous case where we said that the intercept can be interpreted as holding all independent variables at 0. Alpha gives us the expected value of y if everything else is at 0. The expected value of a dichotomous variable that is either 0 or 1 is equal to the proportion of 1s in y, right? And so to kind of illustrate why that is the case, we can think of this as for each we can think of this as kind of conditional on x1 being equal to 0. On average, what is the proportion of 1s, so these red dots, out of all observations where x1 is equal to 0, and on average that expectation is 0.43. So in other words, when x1 is equal to 0, or all, if there were additional control variables included, holding all independent variables at 0, the expected value of our dependent variable is alpha, so it's 0.43. The expected value of a variable that is dichotomous, that only takes values of 0 or 1, is equivalent to the expected proportion of 1s in y, okay? So 0.43 means 43% of those observations have the value of 1, and 67% have the value of 0, right? So and I visualize this here using these kind of stacked bar plot. In expectation, when x1 is equal to 0, the proportion of 1s in y is around 43%. The proportion of 0s, of course, so the dots down here is 67% approximately, okay? So the interpretation is still the same. It's still the expected value of y, conditional on all independent variables being equal to 0. The only difference is that the expected value of y of a dichotomous variable is equivalent of the expected proportion of ones in that variable, right? Now, how to interpret the slope coefficient for our continuous independent variable? Again, it's similar to the cases that we discussed before, just keeping in mind that the expected value of a dichotomous variable is equivalent to the expected proportion of ones, right? So holding everything else constant, a 1 unit increase in x1 is associated with a beta 1 increase or decrease in the proportion of ones in y, right? So I plotted the regression line that we have here with the slope being equal to 0.16, and so our beta 1 coefficient means that as we increase x1 by 1 unit, a 1 unit increase in x1 is associated with a beta 1 increase in the expected value of y. A beta 1 increase in the expected value of y, of course, means that in expectation the proportion of ones in y increases by beta 1. Right, so rather than having 0.43 or 43% ones when x1 is equal to 0, we now have around 60% ones when x1 is equal to 1 in expectation, right? And so based on this and kind of the fact that we can interpret these as kind of changes in proportions or changes in probabilities of observing a 1 rather than a 0 is the reason why this type of model with a dichotomous dependent variable where we run an OLS, a linear regression model, is called a linear probability model, right? And we call this a linear probability model because ultimately we're kind of modeling the change in probability of observing a 1 rather than a 0 in a kind of as a linear function of x1, right? So an increase or decrease in the probability of y being equal to 1 changes with a 1 unit increase in x1 by 100 times beta 1, right? So if the proportion increases by 0.16, that means the probability to observe a 1 increases by 16 percentage points, right? The probability is, instead of 43, it's now 59 or almost 60%, okay? So that's the linear probability model. Of course, later on in the next semester, we'll talk about other maximum likelihood models to kind of take into account that this dichotomous dependent variable is not, that we have a dichotomous dependent variable and we're directly modeling the probability using other types of model and not the linear regression model. But it's important to keep in mind that the regression or the linear probability model, especially when you talk about analyzing results from an experiment, is oftentimes perfectly sufficient and is ultimately easier to interpret as, for example, logit or probit models that we're going to come back to in the next semester in 702, right? Of course, the linear probability model has some disadvantages. In theory, you could have predictions that are, as you see, the example that I'm showing you here is the expected proportion of ones is always between 0 or 1. Of course, if we have a strong relationship between x1 and y, we could have a steeper slope, and as soon as we have a steeper slope, we could have predicted values or expected values that are larger than 1 or smaller than 0, which would essentially mean that the expected value of y is above 1 or below 0, which of course doesn't make sense with the dichotomous dependent variable. But in many applications, especially when the actual probabilities are around 0.5, 0.6 or 0.4, then the linear probability model actually works quite well. All right. So much about dichotomous dependent variable. As I said, we'll come back to other types of models to take into account this data structure where we don't have a continuous dependent variable. We'll also talk about other types of categorical dependent variables, but for now we'll stick with the linear probability model, and now we know how to interpret these coefficients with a dichotomous dependent variable. I have one last case for you that we're going to move on to in the next video, which focuses on changing coefficients and what does it mean if a coefficient changes with changing model specifications.